Now you'll notice it's still not working properly. The smoke's just disappearing as soon as it hits those edges, and disappearing as soon as it hits the bottom edges, and where these forces seem to just end at exact voxel boundaries. And the reason for this is divergence. Divergence is a measure of the imbalance in the velocity field. If we look at each of these individual voxels and we look at how much fluid is going into the voxel or leaving the voxel, we can see whether or not it's having a net gain or a net loss. Now, in a proper incompressible fluid, no voxel will gain or lose fluid in a time step. It'll all be balanced out on the incoming and outgoing. And this still allows for swirls and shears and translation motions. It just takes out any scaling motion that's present in the fluid. So to get rid of this divergence, we need to build a pressure field which represents a contrary force that will cancel out all these ups and downs. The trouble is if you change one of these velocity values on one cell, you end up actually having to affect the divergence in the neighboring cells. So everything gets coupled together on a big massive matrix of equations, and so you need to solve it all at the same time. Now fortunately we have that solver built in. As a matter of fact, it's such a useful solver. We have 3 of them. We have the gas project non-divergent. The vanilla one is the one that was in Houdini 11 in previous versions. We have 2 new versions now, the multi-grid and the variational. So multi-grid is the really fast one, and it also doesn't have as much bells and whistles as the others. It doesn't support free surfaces and actually doesn't support collisions. The project non-divergent is same old. It supports all those things, but the new variational one is a bit more difficult to set up, but is capable of handling a higher accuracy behavior, especially around sloped boundaries. So in this case, we're just going to use multi-grid because we just want speed. And so I wire in a multi-grid, and let's actually look at what our vector field looks like after a few frames here. So I'm going to run forward. And we can see we've got this ugly field where things just aren't moving right, and you know, basically this upwards moving fluid here, the next cell isn't having any fluid leave it, so it just accumulates there. We need something to say stuff has to get out of the way. And this is nicely winding to me because I've not specified a velocity field, so let's do that. And actually I have to, that's right, and rerun it. And now we can see suddenly we actually have what looks like real fluid motion with proper swirls and vortices and everything, and the smoke is actually able to get past those points without all disappearing. So to repeat with pictures, this is a 2D fluid simulation here. The left one is a simple noise, cellular noise of some sort. And you see you've got these points of rarefication, these points of compression, and the center image shows the pressure field that was computed by the project non-divergent, which describes how to counteract those scale effects. And if you apply that pressure field to the velocity field, you get the one on the right, which looks like a nice swirly fluid like you want to see. So there's still something wrong there. If we look at the behavior we had, and especially looking at the velocity field, you can see this big circular blob of upwards moving velocity which actually isn't moving. And that's because we have an Eulerian representation of our velocities. So if we don't do anything to explicitly move or update these velocities, they'll stay fixed in space because they're just sensors. But in the real world, the velocity is a function of the actual particles of the air. So as the air moves from cell to cell, it takes its velocity with it. It transfers its momentum with it. And so to represent this momentum transfer, we need to also advect or move the velocity field by the velocity field. The one thing we do have to be careful to do here is to make sure we move the velocity field before we do the project non-divergent. If we did it after the project non-divergent, then when the original advection of the density field runs, it won't have a fully corrected field because it'll have any of the errors from that advection process. And so here I specify my field as velocity, advect by velocity, and I also turn on allow self-advection because this tells it needs to create some temporary fields to hold it because it's trying to move it by itself. And now we see something that actually rises properly, so we don't have that fixed ball of vertical space, but it actually starts to rise. And I'll turn off the that so we can see a little puff of smoke. So that actually completes my example of a volume-based simulation. We've seen how to add density over time, how to add velocity over time, how to advect those components to get them to move, and also the key step of ensuring everything remains divergent free. So for the next section, we're going to look at building a different type of solver, namely a fluid solver, where we're trying to solve a liquid simulation. We're going to do this instead of in the Eulerian framework. We're going to do it in a much more Lagrangian framework of just storing all of our data on particles. And this is going to be very almost exactly analogous to how the flip solver works in Houdini. So first thing we need is a particle system. In order to make things difficult, I'm going to start with a brand new system. Go and dive into geometry and build a .NET, which I'm not sure if I'll actually ever leave, and go into the .NET and start building a particle system from scratch, because I said I'd do stuff from scratch today, so I'm not going to go use pre-built particle systems. And so I need some particles first of all, so I'll do a SOP geometry. And the SOP geometry has an option to not use an external reference to a SOP, but what's inside itself. So I can actually dive inside the SOP geometry to populate what it has. So in this case, I'm going to put down a box. I'm going to increase its size a bit to be, 3 cubed. And now I'm going to use one of the nice, useful SOPs, points from volume, which takes any object and builds a whole grid of points inside of it. And in this case, I want to increase the scale a bit of the jitter so they're not all perfectly lined up, because I don't like perfectly lined up points. And I'm going to add a scale attribute, so it's got a p-scale storing how big these points are based off the separation I specified. Next I'm going to color them so we have some nice colors. So diving into this VOP SOP, I'm going to grab the position and compare the y value to see if I'm above or below the 0 line. I'm going to use that to drive a color mixer. And so this becomes the bias amount for my color mixer. And there's 2 beautiful colors that are chosen by default there, so I don't need to specify colors. So now I've got pink on the bottom and blue on the top. I also want to add some more attributes here, so I'm just going to create a constant for the velocity and acceleration. This is just so I create those attributes. So now I have something with velocity, acceleration, color, and p-scale. So jumping up now to the DOPS level, I now see I have this SOP geometry, and I want to start actually moving it and stuff, so I'm going to put a multiple solver on it. And how do I want to move it? First I'm going to put just a placeholder merge so I can insert stuff before these integration nodes I'm about to put down. But there are 2 types of integration I want to do, is to add the acceleration into the velocity and add the velocity into the position. So this is just 2 gas linear combinations. So the first one is my XL to V, in which I write to V on the data called geometry, and I add V to acceleration, where acceleration is multiplied by time step. And I do the same thing, except this time it's going to be V to P, where my destination is capital P, and geometry. And I add P to V, and I multiply V by time step. And of course I can hit play now, and nothing will happen because I don't have any velocities yet. So I need something to generate some forces and velocities. So I'll put these in this merge node. The first one I'm going to do is a gas linear combination just to wipe out the acceleration so they're cleared every frame. So destination acceleration, geometry, and if I call this clear accel, and because I haven't specified any sources, it's just going to write it all to 0, which is nice and convenient. Then to build the acceleration, I'm going to use a SOP solver. And again, dive into the SOP solver. And this is a simple VOP SOP. So dive into the VOP SOP. And I can extract now using a vector to float, I can extract my color values. And I'm going to use those colors to determine what type of particles I have. Because I have the, I don't know why it's not displaying it. But anyways, I have the red and the blue particles. So the red ones I want to have go upwards, and the blue ones I want to go downwards. So I can compare the red channel with 0.5. And if it's greater than that, I can use that to control a two-way switcher and create a constant, which is a vector pointing upwards. And I can also negate that to make the constant of the downwards one for the opposite. And I wire that into, well, I should probably add that into acceleration. So add, in case there's any other forces people add that into acceleration. So now I'm adding acceleration based on color. So if I display this all properly, yay, I have the red ones going up, the blue going down, they're accelerating. I'm done. This is a particle system. We're done here. Any questions? Wait, okay. You wanted fluids. You wanted it to interact somehow. So what's the big reason why these are running through each other? Well, it's because they are just each operating entirely independently. We need some system to couple them all together. And if we looked at the velocities of these, we'd see just that divergence we saw before. Namely, on that boundary layer, you have velocities going down and velocities going up. And so those cells would basically be accumulating extra points. And we need some system to say, wait a second, you can't do that. You're going to have to shoot off to the sides or do something to account for this. Now, it happens to be we have a tool that can solve that equation if it's given a big grid data. But in this case, we have a bunch of polygons. And so what we can do is we can copy that polygons, a bunch of particles. So we can copy that particle data onto the grid and then solve it on the grid and then take our solution and copy it back to the particles. And that way we can get a solution for our particle system. And that's the essence of Flip. So let's go about actually doing that. If we want to do this, we want to do it after we've applied any of our accelerations to our velocities, but before we've actually applied our velocities to our positions. So I'm going to just put in a merge node here and make sure it's injected at the right point in this multi-solver list. So it's in the order that I've got them wired up there. So first thing I need to do is create a vector field. And the size of this vector field is irrelevant. What's important is the division size, because I'm going to be resizing this vector field dynamically to always contain wherever my particles are. And I want to have it around the same division size as my particles, which the defaults thankfully are. So I'm going to add a vector field visualization so we can see what happens to this vector field over time, including the bounding box so we can see what size it is. So inside this merge node, the first thing we want to do is resize it. And so I can go here and say I want to resize vel, which I haven't actually named it vel yet, so I better go do that. Data name vel. So I want to resize the vel field according to our geometry. Our geometry being the name of the data that contains the particles. So now when I go forward, we can see we have something that actually nicely, closely fits it. Now in this case, we might actually want a little bit of a slack area around it, so I'll put a 3 voxel border around it, just so we've got a little area around for our sampling. So now what I want to do is I want to copy the particles' velocities into this vector field. And so a gas particle to field will do this. And my destination field will be velocity. Particles is the name of that geometry. And the attribute is V. And if I run this forward, I should probably change the visualization to use streamers and color by direction. And now you can see the green versus the purple streamers showing we have opposite directions meeting in the center there and getting all confused when the particles are running on top of each other. What I also need to do here actually is turn off the max extrapolation cells, and because I want to make sure all the velocities in the space get their values. And I also need to go to the vector field, and I didn't do this on the previous system, but in this case I'm going to switch it to a face